Time travel. It's one of those ideas that refuses to stay inside science fiction. No matter how many times we're told it's impossible, the question keeps coming back. What if it isn't? What if the universe itself already contains the tools, the shortcuts and the loopholes that make time behave in ways we never expected? Because real physics actual experiments, real clocks, and the equations that govern space and time all point to a strange truth. Time doesn't flow the same for everyone. It bends, it stretches, it slows. And once you see how that works, time travel stops being a fantasy and starts becoming a feature of the universe. So today we're going to strip away the fiction and explore what physics actually says about traveling through time. Time travel is one of those ideas that sits right on the edge between science fiction and real physics. We love imagining people jumping into machines, spinning through wormholes, and visiting the distant past or future. But what if I told you that real physics actual equations, real experiments, and proven effects already allow certain kinds of time travel? What if time isn't a rigid line that marches forward, but something flexible, stretchable, and bendable? Something that behaves very differently depending on where you are and how fast you're moving. Because the truth is, physics doesn't treat time as a universal clock. It treats it as a dimension woven into the fabric of space. And once you understand that time travel becomes less magical and more unavoidable. So today, we're going to break down what time really is, how Einstein discovered ways to travel into the future, why traveling to the past is still theoretically possible but wildly complicated, and why some of the biggest paradoxes might not be paradoxes at all. And by the end, you might realize that time travel isn't a question of, is it possible, but a question of what kind of time travel are we talking about? Let's start with a simple question. What is time? We tend to think of time as something separate from space, like an invisible river that carries everything forward. But in physics, time is not separate. It's part of a four-dimensional fabric called space-time. Every moment of your life, every place you've ever been, every direction you've ever walked forward, backward, left, right, up, down, all of it sits inside this four-dimensional structure. You move through space by walking, but you move through time simply by existing. And the incredible thing is that your speed through space affects your speed through time. This idea might sound strange, but it's the core of Einstein's theory of relativity. According to Einstein, the universe has a rule. The speed of light is constant for everyone, no matter how they move. And to keep that rule consistent, the universe adjusts space and time. If you move faster through space, time must slow down for you. If you stay still, time flows normally. The universe balances everything automatically. This leads to one of the most mind-bending truths in physics. Time is not absolute. It's relative. It doesn't tick the same everywhere. And once you accept that, time travel begins to look a lot less like science fiction. Let's look at the simplest kind of time travel, traveling into the future. This kind of time travel has already been observed, measured, and confirmed. And you don't need a time machine. You just need speed or gravity. According to special relativity, if you travel fast enough really fast, your time slows down relative to someone who stays behind. This effect is tiny at normal speeds, but becomes enormous as you approach the speed of light. Imagine you fly a spaceship at near light speed for what feels like 1 year. When you return to Earth, maybe 10 years have passed here. You've effectively traveled into the future. This isn't a theory. We've tested it. Atomic clocks on airplanes tick more slowly than identical clocks on the ground. GPS satellites orbiting Earth experience time differently than we do, and engineers must correct for this every single day, or GPS would be wildly inaccurate. Even the International Space Station astronauts age slightly slower than people on Earth. It's microscopic but real. This is time travel to the future. Not Hollywood time travel, not teleportation, but genuine physical time dilation. But speed isn't the only way to travel through time. Gravity can do it too. In general, relativity gravity isn't a force pulling you downward. It's the curvature of space-time. A massive object bends space-time around it, and that curvature affects time itself. Clocks closer to a massive object tick more slowly than clocks farther away. This means if you live at the bottom floor of a skyscraper, you age slower than someone on the top floor. Not enough to notice, but enough to measure with precise instruments. And near a black hole, time slows dramatically. If you hovered safely near the edge of a supermassive black hole for what felt like a few hours years might pass outside. For everyone else, time would flow normally, but for you, it would slow down to a crawl. The closer you get to the gravitational center, the stronger the effect. At the event horizon, time at least, from an outside observer's perspective, almost stops. This means the universe itself provides natural time machines. Not machines you build, but environments where time flows differently. Traveling into the future is not just possible, it's guaranteed whenever you move fast or experience strong gravity. But what about the real dream traveling into the past? Here is where things get strange. Unlike the future, traveling backward is not something we have observed. But what's surprising is that physics does not strictly forbid it. In fact, Einstein's equations allow solutions that loop back in time, something called closed timelike curves. These curves represent paths through space-time that return to their own starting point. If you follow one, you eventually reach a moment before you left. How could something like that exist? One possibility is a wormhole, a tunnel linking two separate points in space-time. Wormholes are legitimate solutions to Einstein's equations. They're not guaranteed to exist, but they're allowed. The idea is simple. Imagine space-time as a sheet of paper. If you fold the paper so two distant points touch, a wormhole would be the shortcut that connects them. Now here's where time travel enters the picture. If you take one end of a wormhole and move it quickly, say at near light speed, it experiences time dilation. Its time slows relative to the other end. When you bring it back, the two ends of the wormhole are no longer synchronized. One end is older, one is younger. Walk into one end and you walk out at a different time. Go through one direction and you emerge in the future. Go through the other direction and you emerge in the past. This is the closest thing physics has to a time machine. But there's a catch. Wormholes require exotic matter material with negative energy density. We have no evidence such matter exists in large quantities. Quantum physics allows tiny amounts to appear briefly, but nowhere near enough to hold open a wormhole big enough for travel. Black holes offer another possibility. A rotating black hole called a Kerr black hole has a ring-shaped singularity. Some solutions suggest you could travel through it and emerge in another region of space-time, maybe even another era. But these solutions also require ideal conditions that probably don't exist in reality. In practice, the forces near a black hole would tear you apart long before any time-traveling effect could occur. There is also something called a cosmic string, a hypothetical object from the early universe that could warp space-time enough to allow time loops if two strings passed near each other at high speed. But cosmic strings remain hypothetical, and there's no sign that they actually exist. So the mathematics of general relativity leaves the door open for backward time travel. But every possible method requires something we've never seen: exotic matter-perfect wormholes or objects that may not exist. Even if we could overcome those problems, there's a bigger challenge: paradoxes. Backward time travel creates all kinds of logical nightmares. The most famous is the grandfather paradox. You go back in time and prevent your grandparents from meeting. If they never meet, you're never born. If you're never born, you can't go back in time. Which means they do meet. Which means you are born. Which brings you back in time again. It's a loop with no consistent answer. Another paradox is the bootstrap paradox. Imagine you travel back in time with a book. You give the book to a younger version of yourself. That younger version publishes it. The book exists, but it has no true origin. You didn't write it. Your younger self didn't write it. It exists purely because you brought it back. The information appeared out of nowhere. So how does physics deal with these contradictions? One answer is the Novikov self-consistency principle. It says that even if time travel to the past is possible, you can't change the past. The events you try to alter will adjust themselves to prevent contradictions. If you try to stop your grandparents from meeting something, we'll intervene. Your plan fails, or something unexpected happens because the timeline must remain consistent. Another explanation is the many worlds interpretation of quantum mechanics. This idea says that every decision splits the universe into multiple branches. If you travel back in time, you don't change your original timeline. You enter a new one. In that timeline, you could do whatever you want, prevent your birth, meet your younger self, rewrite history, and your original timeline remains untouched. Under this interpretation, time travel doesn't change the past. It creates a new past. Then there's the possibility that the universe simply forbids time travel in subtle ways. Maybe wormholes can exist, but collapse too quickly to be traversable. Maybe exotic matter is impossible to stabilize. Maybe quantum effects always prevent closed time-like curves from forming. Stephen Hawking even proposed something called the chronology protection conjecture, the idea that the universe protects the timeline by destroying any mechanism that would allow backward time travel. But even if traveling into the past turns out to be impossible, something fascinating happens when you look at quantum physics. At the subatomic level, particles don't behave the way we expect. The equations describing them allow certain processes to move backward in time. They allow particles to interfere with themselves as if they had taken multiple paths simultaneously, some of which mathematically go backwards. These aren't literal time travelers, but they show that time symmetry is deeply woven into the universe's laws. So, what does all of this mean? It means that time travel into the future is not only possible, it's happening all the time. Every astronaut, every particle moving near light speed, every clock in orbit is already experiencing it. Time travel into the future is built into the structure of space-time. Backward time travel, on the other hand, lives in a gray zone. It's not strictly forbidden. The equations allow it. But it requires conditions and materials we've never seen. It creates paradoxes we don't fully know how to resolve. And it pushes physics to the edge of what we can understand. Maybe the reason we don't see time travelers from the future is because backward time travel is impossible. Or maybe it's possible, but not in a way humans can ever achieve. Or maybe they're here, but in timelines we can't access. The truth is, time travel is not about machines or tunnels or flashing lights. It's about understanding how the universe works at its deepest level. Time is not a straight line. It bends, it stretches, it responds to energy motion and gravity. And somewhere in that complex geometry lies the possibility, however faint, of stepping outside the normal flow. So the next time you think about time travel, don't imagine DeLorean cars or spinning portals. Imagine space-time itself shifting, bending, twisting. Imagine clocks ticking at different speeds, depending on where they are. Imagine a universe where the past, present, and future are not fixed points, but parts of a flexible structure that we barely understand. Because physics doesn't say time travel is impossible. It simply says the universe plays by rules we are only beginning to uncover. And every time we learn more about those rules, we get a little closer to discovering what time really is and what it means to move through it. That's what physics actually says about time travel. Time travel has always captured our imagination, but the reality is far more fascinating than anything Hollywood has created. The universe already lets us slip into the future through speed and gravity, and its deepest equations still leave the door cracked open for journeys into the past. We may never build a time machine or step into a wormhole or rewrite history, but understanding how time really works shows us something even more incredible. The universe is far stranger, far richer, and far more flexible than we ever imagined. And as physics continues to push deeper into the unknown, we may one day discover that time travel isn't just a story we tell, but a part of the universe we've only just begun to understand. If you enjoyed this explanation and want more deep dives into the mysteries of science, feel free to subscribe and join us for the next exploration. Until then, stay curious, keep questioning, and remember, time doesn't just move forward, it moves with you. Moves.